problem 33 in chapter 5.
Problem 33 in chapter 5.
Mm-hmm.
Oh my goodness, what did I just do? Okay. Okay. Hey, let me get myself in here. Again. Let's see. Oh man, what is it? 8, 4, 5, 3. Yeah. Okay. Okay. So it looks like I have an exponential distribution, right? Is that what the one you're looking at?
Yeah. Yep.
So X is distributed as exponential with parameter lambda equal to an eighth.
Mm-hmm.
Okay. And it says, if Jones buys a used radio, what is the probability that it will be working after an additional 8 years? Okay. So this is saying like, okay, so suppose the radio, and hopefully this will connect back to stuff that I talked about in the lecture. Suppose the radio has already lasted, T0 years. Okay. Are the units in years here?
I think so. Yeah.
Yeah. Okay, so T0 years. Then they're asking us for the probability that X will last at least another 8 years, right?
Mm-hmm.
So will last greater than 8 plus T0, right? Because that would be the total life of the radio, correct?
Mm-hmm.
Given what?
That it's already lasted for 20 years.
Yeah, that X has already lasted for T0 years. But remember that this thing is, what's the key word?
Memoryless?
Yeah, this thing has the memoryless property. Okay, it has the memoryless property.
Mm-hmm.
Which means that this is just going to be the probability that X is what?
Greater than 8?
Yeah. Yes. And that is just going to be equal to e to the minus 8 lambda or something, right?
Mm-hmm. Yeah.
Okay. Because the cumulative distribution function is 1 minus e to the minus lambda x. Okay. And so and here we kind of have the opposite, or we have 1 minus the cumulative distribution
Mm-hmm.
function. So what does that just end up being e to the minus 1?
Yeah. Yeah.
Yeah. Woohoo! Nice. Thank you. The kids are bringing me. Look at this. I got a little pin for my pad. I've been using nothing but my finger for the past 2 weeks. That just came. Amazon said it would be here like 3 days ago, and it still hadn't come. I was worried somebody had ripped it off. But hey, thanks guys. Appreciate it. Woohoo! Yeah. Could you guys, yesterday during my lecture, I was, I kept getting interrupted. I actually, at some point I turned off the video and like, so that you couldn't see how often it was happening, but I was literally talking sometimes while I had Esther, who's 4, just sitting there watching. And then at some point she was asking a couple whispering questions in my ears while I was talk through. And so I eventually just had to pause and say, you know what, you really just need to not be in here right now. Sorry. Like if my brain was having to do 2 things at once. Okay. So you said there's no answer on this one?
No, but that's the answer I got, so.
Yeah.
Okay.
Okay. Okay. Hey, what else do you guys have? Oh, and let me ask you before I forget, while I have, this non-trivial number of people in here. We are having a math candidate come today to do a teaching session in Zoom at 3 p.m. I'm not saying that this absolutely will happen, because I have to defer to those that are more in authority than I am. But if it is possible, or if it is approved for you to come and watch that, would some of you be able to come? Like,
Yeah.
I'd love to.
Me too.
okay, so yeah, I'll send an email to people, and or someone will, I guess.
Mhm.
Someone will send an email just with an invite.
Okay.
All you need, you guys probably have noticed this, but all you need is that special code.
Hmm.
Every website just has like a certain code. Once I figured out that's what was happening, I was like, why am I constantly creating all these new Zoom rooms? I'm just going to permanently have this one, which corresponds to my personal ID. But yeah. So just be on the lookout for that.
Yeah.
I already sent an email out asking if that's all right. So we'll see what's said. Well, what else? What other questions do you have? What other questions do you have? While you're thinking, let me remark, when we get into chapter 6, you're going to have to dust off the old Calc 3 skills. Have you guys all had Calc 3?
Yeah.
Have you had it, Daryl?
Yeah.
Is that a prerequisite for this class? I hope it is.
Yeah.
Not sure.
I think it might be like, it might not be listed explicitly, but maybe to be in the class itself, you have to, there's another prerequisite that depends on Calc 3 or something. But we're going to be doing things like multi-dimensional integrals, because we're going to start looking at not just one variable, but like multiple variables, okay? Like interacting at the same time. We'll have something called a joint distribution for that. And we'll have to integrate that thing over higher dimensional regions, right? So you're going to have to be able to remember how to do some multivariable calculus. And it's actually, it's not that hard to, even if you don't know multivariable calculus, to kind of learn what's happening. But you do have to be careful. Matthew and I were talking about some of that this morning. You can't just willy-nilly like flip limits of integration around. You have to like think carefully about how to reconfigure the limits of integration when you do that. So that's just a word of warning. If you want like a kind of teaser on some of that, you can go look at the discussion Matthew and I had this morning in office hours. It basically was just us trying to sort through how to reverse the limits of integration of something. I think that even though you may not have the context exactly down, that what we're doing will make sense. It's something that you'll remember from Calc 3. So, does that make sense?
Mm-hmm.
Just, that's something that is to come. Okay. All right, what else? Other questions?
With the normal curve and with z-scores, I mean, it's, by the time we get out to like z equals 3 and -3, we've covered most of just about everything. Does it just kind of keep going indefinitely? Like, if there an asymptote there? Like,
Yeah,
can z just be whatever it wants, just you're not going to get that much more as you increase?
Yeah, that's right. Z could be, I mean, and it's kind of like, it's kind of like, for instance, like the geometric random variable.
Mhm.
You say to yourself, okay, the experiment, so like if I'm flipping a coin and I'm waiting for the first heads to appear, in theory, that could go on forever.
Right.
I would have to be really, really lucky, and you would start to get really suspicious. You flipped the 7 trillionth consecutive heads or tails.
Right.
But in theory, that could go on forever.
Okay.
And the same thing is true in this case. It goes on forever, but the likelihood of being that high is so minuscule that
Right.
it's effectively zero eventually. But the main thing I wanted, and this is just important, believe me, the main thing I want you to keep in mind is that any normal distribution can be recast as the standard normal. Hopefully that was clear. And then, and within one standard deviation, you have basically 68.26% of the data. Within 2 standard deviations, it's basically 95.45%. And within 3 standard deviations, it's 99.7. I mean, those numbers are like burned into my cognition permanently because I've used them so often just in practice. I like say, oh yeah, well that's this. And once you get into applications of this stuff, it's just really, really helpful to have that in mind. And the other bit that I want you to be really aware of is the fact that the z-score is the number of standard deviations above or below the mean that you are. Okay? That being able to go back and forth between the x and the z, that's the thing that makes the transition. Z is the number of standard deviations above or below the mean. So those 2 bits are important for sure. Okay? What else? And incidentally, at the very end of the lecture, I made the point that z squared, that z squared, the standard normal squared, has the chi-squared distribution with 1 degree of freedom. So that's where the chi-squared distribution shows up naturally as the square of a standard normal. And the square of a standard normal comes up quite a bit, especially when you get into statistics applications. The squaring a standard normal happens a lot because you oftentimes are trying to estimate the variance of some distribution. And of course, the variance is going to involve the square of the expected value of a random variable, right? So that's where that arises naturally. Okay, what else? What else? This, I mean, isn't this memberless property kind of, I mean, it's kind of surprising, right? It's like, it's like, okay, if I know that it's lasted this long already, what's the probability that it will last another 8 years? Well, it turns out that all I need to say is, well, it's the same as if it were going to last 8 years from the beginning, you know?
Mhm.
So that's sort of an amazing thing to think through, that that's how the exponential distribution behaves. But you can see why that would be relevant to like accidents, right? Like in the actuarial discipline.
Yeah.
Well, they haven't had an accident for 5 years. So what's the probability that they're not going to have an accident for eight years, you know, total? Well, you're just it's basically like, we might as well just start the clock over again. That's just
Right.
the probability that they're not going to have an accident for at least 3 years. Yeah.
Mhm.
So that sort of thing comes up a fair amount in practice. Okay, what else? What else? Hey, can I ask you guys a question about, hang on a second. Can I ask you guys a question about, let me see here, about the test?
Yeah.
Let me see. That you just turned that in on Wednesday, right?
Mhm.
Let me see. I'm pulling it up here. Okay, hang on, I'll leave it in here and I'll share this now. Okay, so like this first problem,
Mhm.
somebody want to talk to me what you were thinking about it? I mean, I'm not saying that you guys were all wrong, but uh, because you weren't. But I was surprised that there seemed to be kind of an even split in terms of how to approach that one. So somebody want to speak to how they approach that first one?
I think that's a binomial.
Okay, you did binomial.
Mhm.
Yeah, that was one of the approaches I saw. Okay, but technically, is this binomial? Matthew, you're smiling. What are you thinking?
I treated it as a hypergeometric.
Yeah. Now, the binomial and hypergeometric aren't going to differ very much.
Mm.
50 million tickets. You know what I'm saying?
Mhm.
And how many are we purchasing? 15.
Yeah.
But technically speaking, for this to truly be binomial, what would I have to allow for the possibility of? Okay, so I have a giant pile of 50 million tickets,
Mhm.
and I'm selecting 15 of them, right?
Mhm.
So in order for it to be binomial, each one of those 15 tickets would have to be seen as a trial that's independent
Oh,
from
yeah.
all the other trials. Does that make sense?
Mhm.
So what would you have to do, Katie, after every selection of a ticket?
replacement?
replace it,
Okay.
and do it again. So
Mhm.
technically, if you use the binomial, you would be allowing for the possibility of selecting. I mean, look, we're not going to select this. I mean, that would just be amazing if that actually happened, right? But so you would technically have to allow for the possibility of selecting the same lottery ticket like multiple times
Right.
in order to have those trials of ticket selection be independent of each other. Does that make sense?
Mm-hmm.
So technically, you should use the hypergeometric distribution, okay?
Mhm.
And the hypergeometric is the one where you had a giant 50 million pool,
Mm-hmm.
good side, and you had a bad side. Remember that?
Mm-hmm.
And you're just counting the number of, the number of good things in a sample of size 15. Okay? So what is the probability of winning at least one prize if you purchase 15 tickets? Well, that would be 1 minus the probability of getting 0 prizes, right? And what would be the probability of getting 0 prizes if you did the hypergeometric distribution? Can we think about that together? How many total samples of size 15 are there from 50 million?
50 million, choose 15.
Yeah. Yeah. 50 million, choose 15. That'd be the denominator.
Mhm.
What would the numerator be if I'm going to select no winners?
45 million, choose 15.
45 million, choose 15. That's exactly right. So it would be, the probability technically would be 1 minus 45 million, choose 15, divided by 50 million, choose 15. Make sense?
Mhm.
But I am telling you, if you compare that probability with the probability you got from the binomial, those are going to be painfully almost the same. Okay, so you guys did 1 minus, so Katie, you did 1 minus what if you did the binomial?
So I actually did it as a sum from x equals 1 to 15.
Oh, but you could have done 1 minus
Right.
the 0 one.
Yeah.
So you could have done 1 minus, what would it be? 1 minus,
15, choose 0.
yeah.
I have to think this one through with 0. Um, 1/10 to the 0, 9/10 to the 15th.
Yeah, so it'd be 1 minus 9/10 to the 15th power.
Yeah. Yeah.
So let's actually compare that. Let me see. Okay. I wonder if it'll do it. I'm actually curious. I think Wolfram Alpha will do it if this won't. But here's 1 minus 9/10 raised to the 15th power. Oops, I have to put equals. Is that? Okay. You guys see my Excel here?
Yeah.
Mhm.
Okay. Or in the other ways, equals 1 minus combin, which is combination. Oh my goodness, is it even going to do this? I don't know. Was it 45 million? Choose what?
15.
Divided by combin 50 million. Choose 15. Right? So I just wanted to give you one where it's like, okay. I mean, I gave you this on purpose because I wanted, I thought that there would be sort of a division in the class in terms of how one would approach it, but the probabilities end up being the same. Right? But they would start to diverge from one another if the pool got smaller and smaller. Does that make sense?
Yeah.
Yeah. So like if there was only 100 tickets, this would still be the probability in the binomial, right?
Right.
But what would it be in this case? There was only 100 tickets. What would this be?
90.
Yeah, because there would be 90 and this would be 100, right?
Hmm.
And now it's starting to make a difference.
Hmm.
Saying. Anyways, I just wanted to point that out.
Yeah.
Hey, what else? Anything else?
How important are the hazard rate functions?
The hazard rate functions.
Yeah.
Okay, can you tell me what page that's on?
201.
Don't they use the right. I mean, I'm not going to make a real big deal about it. They sort of make sense when you think about it. I'm not going to make like a huge deal about it though. I mean, that does come up, right? Because this is all related to the, well, because the hazard rate functions depends on the distribution itself, correct? But in the exponential case, you end up getting a constant. I think that's one nice feature of the exponential distribution. The hazard rate function ends up being the constant lambda. I mean, I'm not going to make a big deal about it in this class, but it does come up, I think, in like, production models, things like that. They might use these hazard rate functions, but they're interesting to think about. Did you have a specific question about that, Matthew?
No, not really.
Okay.
Yeah.
There's another one I didn't talk about is something called the log normal distribution. That comes up quite a bit, but I just didn't know if it was worth spending a lot of time on. In this class, that's on page 210. Those are functions, like at first it just seems like they're blowing up like crazy. And yet when you take the logarithm, you suddenly realize, oh, this thing is just the normal distribution. So that's like these log normal distributions. It's going to come up in practice a fair amount. For instance, like earthquake models that measure intensity. Like the Richter scale is built on this, and I know that the normal distribution is connected to the Richter scale distribution. So log normality is something that comes up in practice quite often. But I just figure that's something that you could think about on your own. I'm just trying to hit the high points here. Okay. What else? What else do you guys have? Well, enjoy the weekend. I'm hoping to get caught up on some things this weekend and Hopefully I can get my pen going here. That'd be great. Maybe it'll improve my handwriting a little bit. But yeah. All right. I'll send an email out to let you guys know if some kind of teaching session in Zoom is imminent,
Okay.
in which student invites would be extended. Okay? Or somebody will send an email.
Okay.
Okay.
Sounds good.
Thank you.
All right, everyone. Have a good
Thanks, Dr.
weekend.
Hammett.
Yep.